Okay, so here we go, number 8. 6.2, number 8. All right, so incidentally, this is very similar to the conical pendulum problem. The only difference is what's providing the centripetal force. All right, so real quick, we'll look at a more careful example later on. But so if I take this B and spin him around like this, so do you guys agree he's kind of a pendulum and that he's swinging back and forth, but it's a circle, right? Good. So there are only 2 forces on the B, yes?
Yes.
So take a second and pause and think about what those 2 forces are. So what do we got? Gravity and tension, right? So if I was to draw that, here's my B. That's the worst B ever drawn by a human being. Deal with it. All right? So gravity is pulling him down. What's the other force on him, you guys? Tension, right? And my tension acts at a weird angle, right?
Yeah.
You guys listen, please. I'm trying to help you with number 8. You guys, like, all of you had your hand up for this. All right, now, what purpose is this tension force serving? It's doing 2 things.
Doesn't allow the force of gravity to pull it down.
Good. Josh just said it doesn't allow the force of gravity to pull the B down. So the idea is there's a vertical component to this force, which is exactly big enough to cancel out my force of gravity, right? Okay, what other purpose is the tension serving? Keeping him going in a circle, right? It's keeping him from going flying off in a straight line, right? So there's also a horizontal component pointed towards the center of the circle, right? So if he's coming around in a circle like this, that tension force is pointed towards the center of the circle, right?
Correct.
Does that make sense?
Yeah.
All right, so we can plug in some quote-unquote numbers. This is mg. So what does the y component of my tension have to be? mg, right? This x component has to be, what's the function, like what's the purpose of this horizontal component? What's it doing to the B?
Oh, it makes it so it doesn't fly off.
Makes it go in a circle. That's my centripetal force. Follow? All right. The airplane problem is the exact same thing, except instead of having a B on a string, it's an airplane flying in a circle. So, let me smallify this. Justin, what's the opposite of embiggen?
Apparently it's small.
Cool. What did you say? Embiggen? I like that. All right. Okay, so here's our airplane. Here's the wings, here's the body of the airplane. There it is. Cool? All right, so there are once again 2 forces acting on the airplane. Gravity is trying to pull it down, right? And the air is holding it up, right? It says something about, assume that the force is just the, I think it calls it aeronautical lift or something, right? In English, air. Air is holding up the plane, and when the plane turns, air pushes the plane to make it turn. Ooh, airplane. Right? So here's my lift force. Not in numbers, but in words. What direction do you think that lift force is acting in? What are you doing this for, Peter? You're making one.
There's 2 components. So like there's the one that's like the B making it spin, and there's the one that's keeping it up in the air.
Good. So there's a vertical component and a horizontal component, but we can't find those components until we know the direction of the vector. So my original question, and then I'll get you, Christine. The original question was, what direction is that lift force acting in? And I don't want a number, I want a description of the direction that it's pointing in. So, Christine, you got an idea? Perpendicular to the plane's wings. Right? Just like an inclined plane problem, right? The idea is the air is underneath pushing up on the wings, right? I shouldn't have said up, but follow?
Yeah.
So the idea is that lift force has 2 components. There's a force of lift in the y direction and a force of lift in the x direction. Does that make sense? Everybody happy? All right, so once again, I know that this is mg. Is the plane moving up or down at all? No, so that means the y component of my lift also has to be mg. And what's the x component of the lift doing? It's creating the centripetal force to get the plane to go in a circle, right? I can't believe I just did that. Follow? Now, there's one other piece of information which I have not yet used, and that is this. The problem tells you that this angle down here is 40 degrees, right? So now we're going to do a little bit of trig. So if this is 40 degrees, doesn't that mean that this angle in here is also 40 degrees? Right? Alternate interior angles. And I know the lift force is perpendicular to the wings, right? So that means that this has got to be 50 degrees, right? Good? So, I'm now looking at a lift force triangle that looks like this. Here's my lift. Here's the lift force in the x direction. Here's the lift force in the y direction. I know this is mg. I know this is mv squared over r. And I know this angle here is 50 degrees. As a quick side note, other than the angle, I haven't put any numbers in here yet. I really want to encourage you guys to try to solve problems this way. All right, so let me pause for a minute. There's a whole bunch of stuff on the board. Did I lose anybody anywhere? Zach?
I was wondering, would it be possible to set this up by using just 9.8 instead?
Totally.
Yeah, I did that and I got the wrong answer, so I guess that I must have done something wrong with the arithmetic or something.
Well, so this is your, the 9.8 is your g, that's your y component. Your x component should be your centripetal acceleration, v squared over r.
Okay, and then you, okay, I must have done something wrong.
Did you put the 50 degrees in the right spot, or did you use?
Yeah, I did use 50.
Okay. All right. Any other questions about this? Yeah, Margaret.
When you do it, do you have to make 480 kilometers per second into...
Yeah. Oh, that's probably your problem, Zach. I had a student last year that every single time that was his mistake. The problem, the velocity of the plane is given to you in kilometers an hour.
No, I did that.
You converted that.
It was 133, so
Okay.
I don't know what...
All right, so is everybody good up to here? I'm going to move on if we're good. Everybody's copacetic? I don't know why I used that word. All right, so here we go. So let's see. That means then that the tangent of 50 degrees should be opposite, which is g, over adjacent, which is, I guess I can do this, over mv squared over r, right? So if you simplify that, it gives you the tangent of 50 equals gr over v squared. And then just, we know everything, right? We know g is 9.8, obviously. I don't know why I'm writing that. We know the velocity is it 133 meters a second if you convert it?
Yeah.
Something like that. And then solve for your r. Cool? All right, any questions with number 8? All right, number 14 is similar to this. So for tonight's homework, you got to do number 14. Same idea. Good? All right. Number 9, I think, was on our list. Oh, great. Yes, this is another really important one. It's actually very, very closely related. Okay, number 9. An old streetcar rounds a flat corner with a radius. So this, oh, hang on one second. Sorry.